Hello, my name is Michael Kaler, and I am the lab manager for the JIAM Diffraction facility located at the University of Tennessee, Knoxville. This video will cover how to use HighScore Plus to identify the phases in a sample. I have a number of other videos that show and explain how to use HighScore Plus for different purposes, such as phase quantification and the determination of crystallite size and microstrain, and the links of these videos can be found in the description below. The first step in phase identification is to load a data file. To do this, we need to go to File, Open. Here we see an XRDML file. That's because I used a pananalytical instrument in order to collect this data. If you have a different type of file, don't worry, HighScore Plus can accommodate different types of files. Let's open it, and we see our data in red. Now the first thing we want to do is determine the background, and we can do that in a couple of different ways. We can go to Treatment, and under Treatment we see a list of different ways that we can treat the data, one of which is determine background. In order to save clicks, I just like to right-click, determine background. Here we see three options: automatic, manual, and by search peaks. I don't really use by search peaks. Manual I use rarely. That's if the background is rather complicated, but most of the time automatic is just fine. We see that we have two parameters here that we can change to try to improve our background, and here we see the background is represented as the green line. Let me turn this down to start. Now bending factor is exactly what it sounds like. It determines how bendy your background is. So as we increase, we see that the green curve begins bending up into the peak more and more. That is not something we want. Granularity changes the distance between points of inflection in the background curve. So a smaller granularity means smaller distance between inflection points. So if we were to increase, it's no longer able to bend up into the peak because the distance from one point of inflection to the next is too great. So typically I like to go around 20 for granularity and then play with bending factor to see what looks best. Let me get this out of the way too. Now in this example, the bending factors all look pretty similar, so I'll just leave it somewhere around 7. You'll notice that you have the option to subtract your background, which will then make the data curve more flat and closer to the x-axis. I don't like to do this for a couple of reasons, one of which is because when you subtract the background, any data points beneath the green line turn into a negative intensity, and Rietveld refinement does not like that. So that's the main reason. Another reason I will touch on here shortly, but for now I will just accept the background as we have it. And we see that the background is changed to a dark green line. The next step is not really required, but it is nice when you're trying to do phase identification. If we right click and go to search peaks, we can start to try to tell the software what is a peak and what isn't a peak, or we'll let the software determine that. We have some parameters here that we could change in order to help the software figure out what is a peak and what's just noise. I don't usually change these. I'll just search peaks. We see a bunch of data markers along the top, so a lot of peaks have obviously been found. So for now I will just accept. We see the peak list now here under peak list. And we will want to go through and make sure that the software didn't make any mistakes. It didn't mark something as a peak that's not, or maybe it just missed a peak. Right off the bat, I see that there is an error here at low angles. It's marking this as a peak, but that's really just background and noise. If we want to get rid of that, we put our cursor over the data marker and hit delete on the keyboard. And now it's gone. We'll right click, zoom back out, and now I will go through and just make sure that no other mistakes have been made. Now a lot of these peaks are rather small, so we'll want to zoom in a little bit. But you'll notice that when we try to zoom, it doesn't really allow us to zoom according to that zoom box that we're drawing. It's making sure that these peaks remain fully in the window. If you want to avoid that, you can just click this button, Zoom Intensity. It is likely somewhere else on your screen than here. This is a highly customizable program, so just look for that button. But now if we zoom, it will zoom in according to the box we draw. So let's start to scroll to the right, look at how well the peaks are marked. A couple of items of note: this blue curve is the calculated pattern, so that's where the computer thinks they're peaks. Red, again, is your data. You see that we have one peak marker here, but it looks like two. If you have these sharp peaks that are about half the intensity of the main peak, then that is likely caused by the two different wavelengths of radiation. This is a K-alpha 1 peak, this is K-alpha 2. All you really need to have marked is one peak for K-alpha 1, so it's okay that there's not a second data marker for this one. Obviously, the calculated and the data pattern don't match up all that well. That's okay for now. We will fix that shortly. We just want to make sure that all of the peaks are actually marked. Here we come into one problem. So this peak is marked, this one is not, and this is very obviously a peak. If we right click, we can insert peak and then tell the computer that there is a peak right there. And now that blue line even matches up better with that red line. If you want to get rid of that option of inserting a peak, all you do is right click, insert peak again, and it's gone. So let's continue on, make sure that no other mistakes are found. Here, this might be a peak, but it might not. It's kind of noisy, so it's hard to tell. This most likely is a peak, so we will just insert one there. Right click, insert again. This might be a peak, hard to tell, so I'll just leave it off for now. Now if we zoom back out, we see here at the bottom a difference plot. If you don't see it there, you can always just right click, show graphics, and then choose difference plot. But we see that a lot of the peaks don't match up, as we saw when we zoomed in. What we get down here is just the difference between the red curve and the blue curve. If we want to improve this fit, all we do is go up here, make sure we're in automatic mode, and then choose default profile fit. And you'll see those differences really start to go away. These peaks are much better fit now. Peak locations are more accurate. We still have some spikes of difference here around the tall peaks, but that's perfectly normal. They are still very nicely fit. So now that we have all of our peaks identified, or as peaks, we can go in and try to determine what phases those peaks belong to. So if we right click, we can go to Search Match, and then we want to edit a restriction set. The first thing I'm going to point out is that we have resulting hits of 412,000 patterns. So that means if we closed and searched, right away it would have to search through 412,000 patterns to find which ones match best with our peaks. Now we use the PDF 4 Plus database, the 2019 version, so it's fully up to date. That's why we have so many patterns. Now that takes a little while. That's a lot of patterns to search through, so we want to begin refining our search parameters so that we can search through fewer patterns. One way we can do this is the Subfiles tab. If we know that we have a ceramic material and all of our faces are ceramic, we can choose that. That cuts down the possible patterns to about 17,000. If we knew we had a carbohydrate, that decreases the number of searchable patterns to 657. So already we're getting rid of a lot of possibilities, and that will help us in our search. You can refine searches based on quality. Star quality is your highest, so if you only want those patterns, you can click that. We see that it greatly decreased our possible patterns. I don't usually do that because you might miss something important. Same thing for skip marked as deleted by ICDD. That might be good a vast majority of the time, but I just like to be able to see all possible patterns. If you know that your sample was, or if your data were collected at ambient pressure and temperature, you can click these to avoid any patterns that were collected at non-ambient pressure and temperature. Crystallography, you can put in crystallography, search parameters. Strings, you can search based off of compound name or mineral name, formula, mineral or zeolite class. A lot of these are useful, but I don't really use them. Subfiles I use occasionally if I'm dealing with something more difficult like a cement or a mineral. Most of the time I just use this chemistry tab. And here we can tell it what elements we believe we have in our material and to ignore all other elements. For instance, when everything is gray like this, it means that everything is possible. So we are searching through every possible pattern. If we start clicking some, one click brings us to this bluish color, so that means only patterns that have at least carbon and or oxygen have to be searched. So that reduces it by quite a bit. If we make them green, then we will only search through patterns that have both carbon and oxygen. If we made them red, then we would search through all patterns except for those containing carbon and oxygen. So in this case, I know that I made a sample that had manganese oxide in it and silicon oxide in it. So I will just choose these three as possibilities, or at least one of, and I will add the rest to none of. So now we will ignore anything in red, any pattern that has an element in red, and only search through patterns that have manganese, silicon, or oxygen in them. And we see that we have 1,428 patterns. So I will close and search. Sometimes this is really quick, sometimes it's a little slow. We do see here elements from XRF. Panalytical makes XRF instruments, so you can test it with that, import the results, and then use that to help you in your search match. But we see that the search match is done, so we need to make sure that we say OK. And here we have a list of possible matches. This is our candidate list. First thing to point out is that we have this score column, and it automatically sorts it based off of this column. A high score means that it's a high probability that this pattern matches what's in your sample. But just because it's a high pattern does not mean that it's guaranteed to be in your sample. You need to check and make sure that it really is. We do that by clicking on the pattern that we're interested in, and we go over here and we see these little lines appear beneath our markers or beneath our red data curve. And that represents the peaks that are contained in this diffraction pattern. We see that sure enough, each peak that is in that diffraction pattern matches up with a peak in our sample. This one looks like it's not, like we're missing it, but we see that the intensity is so low we wouldn't really expect to see it in our pattern. Here, this line extends all the way up and matches about what's in our pattern. So this one, it's not a big deal if we don't see it. If we didn't see this peak, that would be a problem because it's one of the main peaks of that diffraction pattern. Now, if we click it, left click, and drag up, we notice that the markers have now turned dark blue, but we also notice that these little V markers on top of the data markers or the peak markers have disappeared, but only those corresponding to the peaks of silicon oxide. So one reason that search peaks is such a nice feature is that it helps us more quickly determine what peaks we still have to find a match for. We see that after we accepted this as a candidate, it reorganized this list, and now manganese oxide best matches the peaks that remain. If we left click, hold that down, and then drag it up, we now see that those peaks correspond to green, which we see here, and now all of our data markers, the V markers on top, have disappeared. So now we know that all of our peaks have been matched. These are the two phases that are in our material, and we have completed phase identification. Now that does conclude this video. As a reminder, if you would like to learn more about using HighScore Plus, links to my other tutorials can be found in the description below. If you have any questions, please feel free to ask me in the comments section. Thank you, and I hope you have a good day.